Permutation and Combination Lesson 1, the Fundamental Counting Principle. In this unit, we will solve problems involving the application of the fundamental counting principle, permutations, including restrictions and repetitions, and combinations. We will also explore patterns in the expanded form of x plus y to the n and solve problems using the binomial theorem. So, introduction. Joe is shopping for a car. The dealer says that he has 3 different models and that each model is available in 5 different colors. Use a tree diagram to determine how many different choices Joe has. So on the right-hand side here, this is what they call a tree diagram. So we have 3 models there, and each model branches out into your 6 choices of color, with then the choices listed all the way on the right-hand side. So basically, model 1, we have available 6 colors, same thing with model 2. 5 colors, same thing with model 3. Look at the number of choices there are. So in total, there are 15 choices, because we can count 15 choices from the right-hand side there. Look at the different number of choices there are for the model and the number of choices there are for color. How do you use these numbers to arrive at the answer, 15? Well, we could have said we have 3 models times we have 5 choices of color, which gives us 15 choices in general. So the fundamental counting principle, consider a task made up of several stages. Excuse me, if the number of choices for the first stage is A, the number for the second stage is B, the number of choices for the third stage is C, then the number of ways in which the task can be completed is A times B times C. This is what we call the fundamental counting principle. So example 1, a toy manufacturer makes a wooden toy in 3 parts. Part A, the top part may be colored red, white, blue, or pink. Part B, the middle part may be orange, purple, or black. The bottom part may be yellow or green. Determine how many different colored toys can be produced using a tree diagram. So in a tree diagram, we essentially have a branch for each choice. So our first choice would be the top, and we have 4 choices for the top. We have red, we have white, we have blue, or we have pink. The middle part may be orange, purple, or black. So now, from each choice for top, we have 3 choices for middle. So each of these levels has 3 branches coming from it. And now from each of these choices, we have 2 choices for the bottom part. So each of these is going to have 2 more choices, yellow or green. And you get the idea. So we would keep giving 2 more branches for yellow or green. And if we count how many branches we have, we'd have 1, 2, 3, 4, 5, 6. We'd have 2 coming off of each of here, giving us 24 toys in total. Oops. 24 toys in total. Using the fundamental counting principle, I like to start by drawing my blank lines. This is saying how many choices I need to make. So I need to make a choice for the top, the middle, and the bottom. Well, how many choices do I have for each? Well, for the for the top, I have 4 choices. The middle, I have 3 choices. The bottom, I have 2. Multiplying these together gives me the same answer from the tree diagram, 24, in a lot shorter way. So in the previous example, the toy consisted of part 1 and part 2 and part 3. The total number of possible ways was found by multiplication. In an example involving and, the total number of arrangements will be found by multiplying. So a Math 30 quiz consists of 8 multiple choice questions. For each question has 4 choices, A, B, C, or D. How many different sets of answers are possible? So here we need to first decide how many choices do I need to make. Well, there are 8 questions, so that means I need to make 8 choices, or 8 decisions. So I can make 8 lines here. 1, 2, 3, 4, 5, 6, 7, 8. Each one of these is representing a question, right? So for question 1, I need to make a choice. For question 2, for question 3, etc., all the way to question 8. How many choices do I have for each one? Well, each option can be A, B, C, or D. So for each question, I have 4 choices. So I multiply 4 together 8 times, so this is really 4 to the 8, which equals 65,536. Now, sometimes we make restrictions, so it gets a little bit more complicated. So when solving problems involving restrictions, it is important that the restriction is dealt with first, as in the examples below. So Eric has been assigned the task of determining how many odd 4-digit numbers there are. He has been told that numbers such as 5267 is a 4-digit number, whereas 0267 is classified as a 3-digit number. The first step of his work is shown. Explain his reasoning for the number 5. So there's basically two restrictions here. One is that it must be odd, and one is giving us this restriction that we can't have a 0 as the first digit. We know we need to deal with those first. So he came to his restriction of odd and put a 5 here. The reason is this digit can be 1, 3, 5, 7, or 9. Right? We can think of when we do this, we can put numbers 0 to 9 to make 4-digit numbers, but we need to make this an odd 4-digit number. So we have 5 choices for that final spot because it needs to be odd. Remember, to be odd, only the last digit needs to be odd. The second step of his work is shown. Explain his reasoning for the number 9. So his reasoning for 9 here is because the digits that can go there are 1, 2, 3, 4, 5, 6, 7, 8, 9. We cannot have a 0 there because then we'd have a 3-digit number instead of a 4-digit number. Now we can fill in the rest. So we know that he has a 9 in the first spot, a 5 in the last one. Now I have no more restrictions, so I can put any number between 0 and 9 in these middle 2 spots, which gives me 10 choices. When I multiply this all together, that gives me, I have 4,500 odd 4-digit numbers. Eric has now been assigned the task of determining how many odd 4-digit numbers there are which have no repeating digits. Explain why the first step in A is still valid, but why the second step is not. So the last digit must be odd. Remember we said there were 5 possibilities. The first digit we know cannot be 0. But we now have an additional restriction because we know we can't repeat things. So not only can that first digit not be 0, it can't be 0, but it also can't be the last digit. But we also can't repeat the last digit. So now instead of having 9 choices, we have 8 choices. So we can't use 0 there, and we also can't repeat the digit we used in our last spot. So let's look at what our total looks like. So we know the last one, we still have 5 choices, 1, 3, 5, 7, or 9. The first one can't be 0, and it also can't be what we used over here. So we have 8 choices now. Now, this in my original problem was a 10, because I could choose from 10 digits. But I've already used one number here and one number here, so that leaves me with 8 choices. And now, my last spot here, I've already used 1, 2, 3 numbers, so I have 7 left to choose from. Example 4. Car number plates in an African country consist of a letter other than I or O, followed by 3 digits, the first of which cannot be 0, followed by any 2 letters which are not repeated. How many different car number plates can be produced? So the first thing I'm going to decide is how many choices I need to make. And in this case, I need to make 6 choices. So there's 6 characters on these license plates. So now I need to start looking at restrictions. So it says, consists of a letter other than I or O, followed by 3 digits. The first cannot be 0, followed by 2 letters which are not repeated. So it tells me the first one can be any letter other than I or O. Well, there's 26 letters in the alphabet, but we need to eliminate I or O, so that must be 24. Then it says the first number cannot be 0. So I know I can usually choose from 0 to 9, which is 10 choices. But I can't use 0, so that means I only have 9 choices. Then any 2 digits go here, so that's 10 and 10. Doesn't say they can't repeat, so it's 10 and 10. Then I have any 2 letters which are not repeated. So that means I have 26 choices here and 25 choices here. Sorry, I didn't need this multiplications there. So now when I multiply this together, this gives me 14,040,000. So you can see this why in Alberta then we added an extra number because we ran out of license plates. Well, if you add an extra number or an extra letter, you get a lot more availabilities of license plate combinations. Okay, moving on to the next part of the lesson here. There are 2 routes from Pitland to Queensville, 3 routes from Queensville to St. Luke's, and 3 routes from Pitland to Rutherford, and 1 route from Rutherford to St. Luke's. How many routes are there from Pitland to St. Luke's passing through Queensville? So from Pitland to St. Luke's, so that's from P to S, but it's telling me I need to go through Q. So when I look at these, well, I first have 2 choices to get from Pitland to Queensville, and then I have 3 choices to get from Queensville to St. Luke's, so that gives me 6 routes in total. B, how many routes are there from Pitland to St. Luke's passing through Rutherford? Well, first I need to go from Pitland to Rutherford, and I have 3 choices there. Then I continue on from Rutherford to St. Luke's, and I only have 1 choice there, giving me 3 routes in total. C then asks, how many routes are there in total from Pitland to St. Luke's? Well, I had 6 routes if I went through Queensville, plus I had 3 more routes if I went through Rutherford, so that is 6 plus 3, which is 9 routes. So in part C, we could travel from P to S via Q, or from P to S via R. The total number of routes was found by adding the answer in A to the answer in B. In any example involving OR, the total of arrangements are found by adding. 6. The telephone numbers allocated to subscribers in a rural area consist of one of the following. The digits 3, 4, 5, followed by any 3 further digits, or the digit 2, followed by one of the digits 1 to 5, followed by any 3 further digits. How many different telephone numbers are possible? So this OR right here tells us we're basically going to calculate the one, calculate the other, and add them together. So our first choice said the digits 3, 4, 5, followed by any 3 digits. So that means in that case, we are really making 3 decisions. It's any 3 digits, so that means we have 10 choices for each one. So that gives us 1,000 possibilities for telephone numbers that start with 3, 4, 5 and followed by any 3 digits. Or means we're going to add. We have the digit 2 followed by one of the digits 1 to 5 followed by any 3 digits. So now the digit 2 is chosen for me, but now I have 4 choices to make because I can have, first of all, here one of the digits from 1 to 5, so that's 5 choices followed by any 3 digits. So now I have 10, 10, and 10. Well, this gives me a total of 5,000 telephone numbers. Adding them together means in total I have 6,000 choices. So example 7. Consider example 3 in which Eric was asked to determine how many odd 4-digit numbers there are. As an extension to his assignment, Eric has been asked to determine how many even 4-digit numbers there are, and how many even 4-digit numbers there are with no repeated digits. Determine the answer to part I. So again here, this is a 4-digit number, so I have 4 blanks I need to fill in because I have 4 choices to make. Now again, this needs to be even, so I'm going to start with that restriction. So remember, even numbers end in 0, 2, 4, 6, or 8, so I have 5 choices there. Now for part I, we don't need to worry about repetition, so I just need to remember that my first digit can't be 0, so that means I have 9 choices, and then any choices for the middle 2. So this gives me 4,500. For B, Eric started his answer to I as shown below, but he was not sure how to fill in the first space in his work. Explain why he needs to consider 2 separate cases to solve the problem. So remember that now we're saying we can't repeat. So in the original problem, we had 5 choices here, 1, 3, 5, 7, or 9. So I said I used up 1 digit there, plus this one can't be 0. However, when we're working with even numbers, there is the possibility that 0 is our last digit, which means if 0 is the last digit, we have still 9 choices for the first one. But if 2, 4, 6, or 8 is the last digit, that means we have 8 choices. So we always know that the first digit can't be 0, but if our last digit was 0, that means we haven't used any of our options up, so we still have 9 choices. However, if our last digit was 2, 4, 6, or 8, that means we can not repeat that digit, plus we can't have 0. So to determine the answer, this is if the last digit is 0, we have, now we only have 1 choice for our last one because it has to be 0. Now we have 9 choices for our first one because we just know it can't be 0. We are not repeating, so we've still used up 2 numbers and then 3. So that gives us 504 even numbers that end in 0 with no repeats. If the last digit is not 0, so if the last digit is not 0, we now have 8 choices here. But this also changes our last option because now we don't have 5 choices, we only have 4 because we're saying this must be 2, 4, 6, or 8. And the middle 2 stay the same, which gives us 1,792. So now to get our total, we would add them together. So this gives us a total of 2,296. Okay, last example. Consider the number of distinguishable 4-letter arrangements that can be formed from the word English. Note there's an implication that each of the letters in the word English only occurs once and cannot be repeated. Determine the number of distinguishables, that means different, right? 4-letter arrangements that can be formed from the word English. Part A, any letter can be in any position. So I'm making 4-letter words, so that means I have 4 decisions to make. How many letters do I have to choose from? Well, here I have 7 letters in the word English. So my choice is 7. Once I've used a letter up, I can't reuse it. So it's going to be 7, 6, 5, 4. So you have to think that I'm physically picking up these letters and moving them around, kind of like Scrabble tiles. So once I've placed one, I can't duplicate it and place it somewhere else. What about if the first letter must be E? Well, I'm still doing 4-letter words, so I still have 4 decisions to make. But now I've been told the first letter must be E. There's only 1 E in English, so I only have 1 choice for the first letter. Then all I know is that I can't repeat letters because I've used up that E tile. So this gives me 6, 5, 4, which gives me 120 options. Sorry, I never finished calculating this one. This one was 840. C, the first and last letters must be vowels. So this is when we need to think hard to English. Hopefully we all remember what a vowel is. Tells us the first and last letter must be vowels. Well, the only vowels in English are E and I, so that gives me 2 choices for the first one. And I can't repeat a letter, so that means I only have 1 for the last one. You could flip these as well. It wouldn't matter which one was 1 and which was 2. I've used up 2 letters now, so I have 5 and 4 choices left for the last 2, which is 40. And what about if the word contains G? So the word is in quotation marks because, of course, these are just letter arrangements. They're not necessarily a word. Well, here we need to consider 4 different options depending on where the G goes. If the G goes in the first spot, we have 1 choice for the first and then 6, 5, 4, which gives us 120. If the G is in the second spot, the 1 goes in the second spot and our 6, 5, 4 go in the other spots. And same idea now, if G is in the third spot, I fill in the 6, 5, 4. So you're going to see that these all are going to equal 120. So you didn't really need to lay it out 4 separate times. My last option is if the G is in the last spot, and 6, 5, 4. So to get my total, I then added these together, which gives me 408. Okay, and that's the end of lesson 1.